as we discussed, thermodynamics simply means heat in motion, or I can say it is a relationship between heat energy and mechanical work. And this concept basically applicable for the mechanical field, because we are dealing with engines where the piston moves. I told you, piston moves. That means because of heat energy, the piston is moving, right? And it drives the car or any automobile, anyway. But we are not mechanical engineers, we are metallurgical engineers, right? So we basically deal with chemical reactions because we want to produce a metal from an ore or from a mineral, right? We have to do some chemical reaction. We have to check whether that reaction is happening or not, whether it is possible or not. That is called feasibility. That is the main concept of thermodynamics. Whether that particular metal extraction or whether that particular refining of metal, impure metal, is feasible or not. So this is the main entire concept of thermodynamics. You can also write it if you want, right? So thermodynamics tells you whether the process, the chemical process or the physical process is feasible or not. So there are certain concepts which will tell you, right? We'll discuss that in coming lecture. So this is the main entire concept. Right? So in the simple way, I can also say thermodynamics means here the change in heat energy or change in energy accompanying with physical change and chemical change. Right? Change in the energy will change, right? Due to change in physical process or maybe some chemical process. Okay? And also I can say, if something is not absorbed, suppose I take one metal and I take another metal, or I take one metal and I take carbon, for example. I take one oxide and one carbon. I put it together, right? So whether that oxide will react with carbon, that can be discussed by this thermodynamic concept. Thermodynamics will tell you whether that oxide will be reduced by the carbon or not to give you a metal. That is a very good concept, right? So thermodynamics tells about the feasibility of the process, whether it is physical process or whether it is chemical process, right? Is it okay? The simple term you can write what is thermodynamics. Okay. Suppose, for example, let me give you. Suppose you want to extract iron. For example, you want to have an iron first, because you cannot make steel directly. You have to produce an iron first. So to produce an iron, you need a ore of iron, of course, and that is hematite. You know that from this group, you know hematite is and magnetite is also, but hematite is the main ore of iron. So that is basically what Fe2O3, right? So now you react the Fe2O3 with carbon. Carbon is the reductant, right? Reductant function is what? It will take away the oxygen from the Fe2O3 because it forms a more stable oxide, that is CO or CO2. Okay, right? So this formation of CO or CO2 will happen or not, or whether this Fe2O3 will become Fe or not, that will be decided by this thermodynamics. So thermodynamics will tell you the feasibility of this reaction, particular, or any kind of reaction. Okay. Similarly, after producing iron, it will be not pure iron. It is impure iron basically. Lot of impurities will be there. Maybe like for example, phosphorus will be there as impurity, your sulfur will be there as impurity, carbon will be there as impurity, manganese will be there as impurity. But you want a pure iron basically. You cannot produce 100% pure iron, but still you want to produce it. So you have to do again some kind of reaction, and that reaction is feasible or not, again thermodynamics will tell you. That means you can able to purify the metal or not, that thermodynamics will tell you. Okay? I'll give you an example later. Is it fine after this? So thermodynamics always tells about the feasibility of a process, whether it is chemical or whether, as I told, if you remember, you take a piece of iron in the room temperature, it will be in which crystal structure? Body centered cubic, I told, right? Body centered cubic means atoms will be at the corner of the cube and one atom will be at the center of the cube. Is it okay? But the moment you take it to high temperature, entire structure will break down. Again, the atoms will arrange in another kind of crystal structure, that is FCC, face-centered cubic. So whether it will happen or not, whether the BCC will become FCC or FCC will again become BCC, that can be talked about by thermodynamics. So it is a physical change, right? Atoms are moving just. We are not doing any kind of reaction here. The atoms are breaking down and moving. Right? This process is called diffusion actually, technically. Atoms are diffusing because of temperature difference. Right? So these are certain examples. Okay, so I can also correlate, as I told, heat in motion or energy in motion. So in other way I can say, for example, let me give an example. Physical process. You take out a cube of ice from the refrigerator and put it on the table here, right? So what will happen after some time? It will start melting, right? It was earlier solid and it become liquid. There is a physical change. Okay? There is a physical change. So what happens? Why this physical change is happening? Because it is absorbing the heat from the atmosphere. Okay, it is absorbed. So heat is moving now from the atmosphere into the ice. Then only it is becoming a liquid. So heat is in motion now, of course. That means heat is in motion here means either heat will be absorbed or maybe released by the system. So here the system is ice cube, which is absorbing the heat from the surrounding. Okay, then now it becomes a liquid. And this process is spontaneous or not spontaneous? Spontaneous, of course. So automatically it will happen. Nothing, you have to do nothing. Automatically it will make. But maybe if you take it to Russia, for example, make some chance it will not happen. Because temperature is different there, right? Russia is very cold, maybe minus 30 degree, minus 40 degree, depending upon the location. Basically, Russia is very cold country, right? So it may not. So that means you should understand one of the important parameters of thermodynamics is temperature. Of course, but temperature of India and Russia is very different, right? Okay. As an example, I can give you, for example, you want heat energy by burning a wood, for example. Is it spontaneous or non-spontaneous? Not spontaneous. Because you have to give some thermal energy to the wood first, then it will undergo combustion, then only it will release the heat energy. So it is non-spontaneous. And you have to remember, most of the natural processes are always spontaneous. Most of them. You go to a like hill station right now. So water is flowing continuously from the hilltop. It is happening spontaneously. You do not have to do anything. Right? Why? Because of potential difference in the physics. Water over a tank is at high potential, right? MgH, and to the ground it is less. So automatically it is flowing down. You do not have to do anything. It is a spontaneous process. So it is natural, no? Water is flowing, it is a natural process. Melting of ice, it is a natural process. You can say. Suppose, have you seen the camphor? Right, camphor, right? If you put the camphor somewhere, if you take out the camphor from the packets and put it somewhere inside your clothes or somewhere else, right? After some weeks, you find there will be no camphor at all. Right? Or if you regularly monitor it, you will see the size of the camphor will reduce slowly, and finally it will disappear. And this process is called what? Sublimation. Right? The solid is directly converted into gas phase without moving into the liquid. Okay? If it was solid and it become gas, it disappeared in the atmosphere. It is also a spontaneous process. Now you do not have to do anything. Here what is happening? What happened to the heat? Heat is getting absorbed by the camphor. Heat is moving into the system. Okay? So heat is in motion, right? So you understand how I am correlating. Heat is in motion. So heat will either absorb or release. Let me give another example. You take metal and take the metal to above the melting point. So what will happen? It will become molten. Of course. Above the melting point, the solid metal will become liquid, right? Now, this process is non-spontaneous, of course, because you have to provide heat energy to the metal so that the solid will become liquid. That means it is absorbed by the metal first, then it becomes liquid. But the moment you will provide the heat energy, what will happen? Again, it will cool down and it will become solid again. It releases the heat out of the system. Heat is in motion, right? That's what solidification technically. Liquid metal becomes solid. But it will become spontaneous if the temperature is below melting point. Then liquid becomes solid. Otherwise it will not happen. If you constantly providing heat and the temperature is above melting point, it will never become solid. You have to bring the temperature below the melting point. Then only it will automatically become solid. With time. You take out the heat from the system and it becomes solid. Okay. So there is a particular concept called solidification. I am going to teach you that in physical mechanics there. Okay. So you understood the concept of this spontaneous process. You can write some examples also, like sublimation of camphor, melting of ice. These are spontaneous processes. Non-spontaneous process, conversion is a code. Many examples are there. But we will spend more time here. This one, feasibility, equilibrium, and driving force, because this term will come many times in thermodynamics. And driving force also. Feasibility, okay, fine, as I told, feasibility. Feasibility term, you understood? Feasibility means whether some chemical reaction is happening or not, feasible or not. That is called feasibility. Okay. So, okay, let me write one example. Phosphorus made with FeO will give you what it will give you? Plus Fe. So this is one of the simplest reaction I am writing here. So phosphorus is in metal, this FeO is in slag. I will tell you what is metal slag means. This is slag again, and this is metal. And here this is 2P and 5. Fine. This is one of the simplest reaction I am writing. This reaction actually basically happens in steel making process. See, I told you this thermodynamics is applicable to all the subjects in the metallurgy. It is an applied subject. You can apply thermodynamics to iron making, you can apply thermodynamics to steel making. So that's why I am giving this example. This will help you during the steel making subject. Right? This reaction happens in the steel making process. As I told, we cannot produce directly steel from the iron ore. We have to produce first iron, that will be impure iron, then we need to refine it, finally we will get a steel. So steel is a refined product. Right? And I told what are the impurities in the iron first. You remember? As I told, carbon will be there. Right? These are the impurities. Carbon, sulfur, silicon, manganese, phosphorus. These are the impurities present in the iron. The moment you extract iron from the iron ore, these impurities by default will be there. These impurities come from ore itself. It is there in the ore, and maybe it will be there in some reductant carbon itself, because we are using charcoal or we are using coke as a reductant. So from that charcoal and coke, some impurities will also come. Some impurities will come from directly or from reductant also, some impurities. Finally you get iron with these impurities. And you want to produce steel, so you have to remove all. This one, of course. I am giving just example of this one right now to make you understand about the thermodynamics concept, right? You want to remove this phosphorus. You have to remember this bracket. This kind of bracket means this is present in metal. This kind of bracket means this is present in slag phase. Metal is one phase, slag is another phase. When see. For example, there is a concept called pyrometallurgy. Pyro means heat, metallurgy means extraction. So, best example of pyrometallurgy is extraction of iron from the iron ore. Why? Because to extract iron from the iron ore, we are providing some heat energy. We are taking the ore to high temperature. So that is a pyrometallurgical process, right? Pyrometallurgical extraction process. We have other metallurgy, that is hydro and electro. We will not discuss that because that is not related to this. So you understood my point, right? After this, so you will end up with phosphorus present in the iron, and you want to produce steel out of it. You have to remove the phosphorus. So how phosphorus will be removed? This is very interesting. See, you have to understand this. This is very good concept. extraction of iron is a reduction process, but converting iron into steel is a oxidation process. You have to remember, this is a very important question they ask during placement. What is the difference between iron making and steel making? Iron making means it is a reduction process. We are reducing Fe2O3 to Fe. Reduction means removal of oxygen. Is it fine? We are getting our Fe2O3 will become Fe. That means we are removing the oxygen. It is a reduction process. Okay. So iron making is a reduction process. Steel making is an oxidation process. Oxidation means we are intentionally adding oxygen again. Just opposite. Why we do that? Can you tell me why we do that? Just look at the reaction analysis. The point is, we are intentionally adding oxygen during steel making so that these impurities move apart from this one. Forget about sulfur. This one, this one, this one, this one. If you provide oxygen, they will become oxide. P become P2O5, carbon becomes CO, silicon becomes SiO2, and sorry, this is not Mg, this is Mn. Mn. This is Mn actually, not Mn. Manganese. Mn become MnO2 or MnO. So it will become oxide. The moment you are providing oxide during steel making. So once it will become oxide, it will not stay in the iron. It will simply move to the slag. I told two phases are there. Yes. Two phases will form. Inside the reactor, two phases will form. One is slag, which will remain on the top, and one is the metal phase. This is metal phase, and this is slag phase. Initially there will be no slag at all. When you start the process, steel making process, only impure metal will be there. But the moment you start providing oxygen, slag will start forming, right? And this slag it will form because of flux. Have you ever heard about this term? No? Any idea? Flux plus gangue. Or gangue means these are impurities actually. Impurities. Impurities in what? In metal. Flux. Best example I think between iron making, the best flux is line. This is the flux in the iron making. Because I told you I am writing a simple Fe2O3, have a name. It will react with carbon. Also you need a flux. Fine? Because Fe2O3 is not pure initially. It will also having some gangue. As I told you, how these impurities are coming? These impurities are coming from the gangue which is present in the ore itself. This is your ore. Okay. Silica will be there, aluminium will be there basically as a gangue, and some phosphorus will be there. Some phosphorus also comes from coke, this carbon, and sulfur will be here. Most of the sulfur will be here. That will come from, and finally you end up with what? Fe, metal plus slag. This is a metal, but this is impure. Okay. Why impure? You understood. Sulfur will be there, phosphorus will be there, silicon will be there, carbon will be there, and manganese will be there. So this is impure iron. Will get. Okay. And finally, later you have to convert this into steel, and you have to remove phosphorus. I am giving a simple example of phosphorus here to make you understand about the thermodynamic concept here, or equilibrium concept. I will discuss that. So, what exactly happened? See, now this one. Impure Fe, impure Fe, so you provide oxygen, and this is in molten state, you have to remember. Actually this is molten iron, this is molten iron and molten slag. Technically this is called smelting. This is called smelting. Smelting means reduction will happen and melting will happen. At the end, you will get molten things. Initially, the raw materials, these raw materials are in solid actually. After metal extraction, you will end up with liquid things, liquid products. That is for smelting, because reduction is happening and melting is also happening. And pyrometallurgy process means we have provided the heat energy externally. Okay. You are getting my point? Up to this it is clear? So, in the next stage, I told steel making. No? Steel making, we need to remove what? all these things, carbon, silicon, manganese, phosphorus. Actually, so that means I have iron, I have also carbon, I have also silicon, I have also manganese and phosphorus. Okay. But your question will be, if we provide oxygen again iron also become oxide. Of course, temperature is high. Iron also take the oxide and become again oxide. So what is the meaning of doing this? Initially it was oxide. Again we are providing oxygen to make it oxide. Okay, you understand my point? Fe again may become Fe2O3 because of presence of oxygen at high temperature. Okay, but this is a preferential reaction. The reaction is preferential. That means some of the element has high affinity to oxygen compared to that of iron. So steel making is a preferential reaction. So what will happen? This will react with this in a little amount, but this will react more with this, more with this, more with this, and more with this. Preferential reaction will happen. Most of the oxygen will be reacting with these things because they form more stable oxide. Carbon form more stable oxide, that is CO. Silicon also form more stable oxide, that is SiO2. Phosphorus also form more stable oxide, P2O5. But Fe also form oxide, but it is less stable compared to these oxides. Is it fine up to this? So preferentially the oxide is reacting with the impurities, not with the main metal. It will react, but in a little amount. Okay. And also you have to remember, whenever oxides will be there, sulfides will be there, or silicate will be there, or any kind of compound will be there, they will not stay in the metal phase. They will by default move to the slag. But if any impurities will be in metallic phase, like carbon, phosphorus, they are metal now, right? They will by default will move to the metallic phase. So this is another concept you have to remember. See, thermodynamics I told it is related, it is connecting with all the things. Physical metallurgy, your extractive metallurgy. So I am talking about extractive metallurgy right now. So you understood my point? So you see, that means you have, initially you can see, let me clarify, these are the impurities present in the ore itself earlier. Due to reaction with carbon, they have become silicon. They have become, actually this is very stable oxide, it will not reduce basically. Some of the silica will also not reduce, but some of the silica will reduce to silicon. So silicon is moving to iron because it becomes silicon now. Similarly, P2O5 also get reduced to P, so it moves to the metal. So finally, that's why you end up with this impurities. This is the concept you have to remember. If something is in compound form, it will remain in slag phase. If something will be in metallic form or elemental form, it will remain in the metallic phase. Fine? So now you have an impure metal and you want to purify it, you want to remove the phosphorus. That means you need to convert the phosphorus again into P2O5. Why? Once it will become P2O5, what will happen? It will move to slag. So this is the way of refining. In pyrometallurgical extraction processes or refining processes, we always use high temperature, we always produce liquid things, liquid products, that is metal and slag. Right? If you want to send something to slag, convert it into oxide, convert it into sulfide, convert it into silicates, it will automatically move. Fine? But by chance if it will get reduced to metallic form or elemental form, it will not stay again in the slag, it will come back to the metal. Okay. Up to this you understood, right? So the point is oxygen will react with phosphorus to become P2O5. P2O5 will move to the slag phase, it is removed. But also I told some of the oxygen also react with Fe to form FeO. Right? That reaction I have written here. See, FeO. So once Fe will become FeO, where it will stay? It is still making process. Slag. Very good. That means some of the FeO will migrate to the slag phase. And FeO also provide oxygen to phosphorus. And that is the reaction here I have written. Because you want to remove the phosphorus, you have to convert the phosphorus into P2O5. Because it will become oxide, then it will move to the slag phase. Automatically it will be removed by forming oxide. So two things are happening. One is direct reaction of oxygen with the P2 phosphorus, and another reaction is the FeO which are already formed and move to the slag phase. That also reacts with the phosphorus. And why this reaction happens? Can you tell me? Already I told you why this reaction is. That means because P2O5 form more stable oxide compared to Fu. Or in other way I can say phosphorus have more reactivity towards oxygen compared to iron. Okay. See, this again is very interesting. This you have lose some iron in form of Fu, but you can recover again the iron by this reaction, because this iron will move to where? Metal. Okay, but you have sent the phosphorus to slag by forming P2O5, and this is one of the reaction. Okay, and there is a concept called, you remember, activity. These are all the concepts we'll discuss later. So this, I am giving an example: activity and chemical potential. Chemical potential. These are nearly same things, not exactly same, but closely same thing. Activity and chemical potential. For example, in this classroom, let me give a normal example. In the classroom, lot of people we are here, right? The moment I will open the door, you can move out of this room, right? So I can say, since the concentration of people here is more, so activity is more in this room compared to the outside. Okay. So where activity will be more, the elements always migrates where the activity is less. You understand my point? Or in other way, chemical potential. So since the concentration of people are here, I can say the chemical potential is higher in this room right now compared to the outside. So what happens? You can easily move from here to there. Okay? So but a time will come if more of the people will come out from this room. The concentration of people will be higher in outside than compared to this. Again, you can also move into this. This may happen. Why I am correlating this? Initially, phosphorus is here in the metal, and you want to send it to this phase, slag. You want to remove it, reduce it. It will become P2O5. So, in other way, I can say initially the activity of phosphorus was more in the metal, or chemical potential of the phosphorus was more in the metal phase. So that's why it is moving to the slag, so that the chemical potential can be reduced or the activity can be reduced. But with time, what will happen? The more amount of phosphorus will remove. So what will happen? Again, the activity or chemical potential of phosphorus will be higher in the slag phase, right? So again, it may come back to your metal, but you don't want that, no? You want to remove the phosphorus. You don't want your phosphorus again will come back to the metal, into your steel. Okay. So basically, activity depends upon the concentration and other phenomena also, like depend on pressure and other things, temperature also, and some chemicals also. We will discuss that later. You understood up to this? It is okay. So what can be done? Earlier activity of phosphorus was higher here. Later the phosphorus activity has increased here, so the phosphorus may again come back. It is going like this, again it may come back. So you want to stop it. So what can be done? You want to then, if you want to stop the phosphorus to come back again into the metal, you have to do what? You have to reduce the chemical potential of the phosphorus in the slag so that it will not come back. Or you have to reduce the activity of phosphorus in the slag so that it will not come back again. So that's why you are adding lime into the process. In steel making process, also we are adding a flux. Same. Like in iron making, we are adding lime as a flux. Similarly, in steel making also, we are intentionally adding lime. So lime is which kind of oxide? Basic or acidic? Basic oxide is a very strong basic oxide. All metal oxides are basic in nature. If you react a metal to oxygen, it will form a basic oxide. But P2O5 is acidic or basic? P2O5 is an acidic oxide actually. You have to remember. This is a very important line. For placement it will help you, or during your GATE exam also it will help you. Whatever I am teaching right now is important for your GATE exam. You will definitely get a question from this in your exam. P2O5 is a acidic oxide Lime is a basic oxide. So what will happen? The reaction will happen between them, of course, because they are opposite in nature, right? So there will be a strong bond between lime and P2O5. Dicalcium phosphate. It is called dicalcium phosphate or calcium phosphate. So once it will form dicalcium phosphate or calcium phosphate, the activity of phosphorus will go down in the slag, or the chemical potential will strongly reduce. So what happened? Chemical potential is reduced in the slag now, in the of phosphorus. It cannot come back. It will stay there. But if you do not add any kind of lime, phosphorus will go as a P2O5 into the slag. Again, it will come reduced by carbon or by some other metals to become phosphorus and come back. You didn't ask me how it will come back unless until it will become P. It cannot come back. Carbon is available. I told you, see, carbon is there in the metal. Other metals are also there. Other metals may also react with P2O5 to become P. Or carbon react with P2O5 to become P. It may come back again into the metal. But you don't want that. You want to remove as much as phosphorus. So you add a basic oxide. Basic oxide strongly react with acidic oxide to form a strong bond. That is dicalcium phosphate. So the chemical activity or the chemical potential will reduce drastically. It cannot come back. But interesting point is what? Now see, you are reducing the chemical potential. The chemical potential or activity. How? By adding lime. It forms dicalcium phosphate. So once dicalcium phosphate will form, what will happen? Chemical potential is reduced here of the phosphorus. So you can send more phosphorus again, because activity or chemical potential of phosphorus is more again here, because it is reduced here, no? Again more phosphorus will migrate to the slag. In this way you can remove lot of phosphorus. Is it okay, or shall I tell you again? Your main priority is to remove the impurities because you want to produce a steel. I just give an example of phosphorus here, right? Again let me tell you quickly. Initially you have an impure iron, you want to make a steel. That process is oxidation process because we are providing oxygen, right? So oxygen will directly react with phosphorus to form P2O5. Now phosphorus become oxide, so it will migrate to the slag phase. So lot of phosphorus is removed now. Again also some FeO will be forming. That FeO also reacts with phosphorus to form P2O5. Again lot of phosphorus will move to the slag phase. But since the concentration of phosphorus is increasing in the slag, activity of phosphorus will move again become higher in the slag phase. So it may come again back into the metal by reduction. But you don't want that. You want your phosphorus to be staying in the slag phase. So you are adding lime. So lime is a basic oxide. It will react with P2O5 to form a strong, stable compound. And the chemical potential or the activity will strongly reduce. So again, there will be a difference in the, why I am saying, the simple concept is, if you want to migrate something from one phase to another, you have to maintain a difference in chemical potential or difference in activity. Okay? Earlier there is a difference in activity, that's why phosphorus is moving. Again you are reducing the chemical potential and activity by adding lime. So again there is a difference in chemical potential or difference in activity, again some phosphorus will move. And this is called shifting of equilibrium. If you remember, you have studied Lee-Chatelier principle, right? So that concept is applicable here right now. Lee-Chatelier principle, right? Lee-Chatelier principle tells what? In simple word, can you tell me? Just in simple word, I don't want the definition. Yes. What exactly it means? You take any reaction, reactant will be there and product will be there. Okay? Then how Lee-Chatelier will be on? Form. Then okay, sit down. Okay, see this reaction. These are the reactants. These are the products. Okay. The reactant will form product first. So reaction is happening in this direction. Okay. Reaction is happening in this direction. More product will form. But after some time, the rate of forward reaction and the rate of backward reaction will become equal. Earlier the rate of forward reaction was higher. That means the equilibrium was shifted in this direction initially. So more product is forming. But a time will come, the rate of forward reaction and rate of backward reaction will become equal. So that condition is called equilibrium condition. Okay? Equilibrium condition means what? The rate of forward reaction will be equal to rate of backward reaction. That means phosphorus will form P2O5, again P2O5 will form phosphorus. Phosphorus will form P2O5, it will go on continue. Once equilibrium will reach. But unless equilibrium will reach, more P2O5 will start forming. More products will form. But a time will come they will reach equilibrium. But you cannot able to see that. You can able to see the P2O5 only. Right? Or some amount of phosphorus will be there. But that reaction will be happening microscopically. I am saying microscopically. But macroscopically you cannot able to see. So why I discuss this one? Because there is a concept called equilibrium. Equilibrium simply means macroscopically there will be no change in the system. If you want, you can write this is a very important line. Macroscopically there will be no change in the system. Here no change in the system means no product will form. Or reaction will not happen further. Okay? Select it again. Macroscopically there will be no change. But microscopically happening now because forward reaction is happening, backward reaction is happening, but they are equal. It is really happening inside. But you cannot able to see that. So macroscopically everything is constant now. Macroscopically there will be no change. That is called equilibrium. Yeah, you have any question then? Oh yeah, sure. Next, I can correlate. Suppose there will be definitely get a question from this. What do you understand by equilibrium of a process, or equilibrium of a extraction process, or equilibrium of a refining process? What do you understand? You can write in your own notes. Equilibrium of a chemical process means the reaction the rate of forward reaction is equal to rate of backward reaction, and macroscopically you cannot able to see any further change. Whatever product is formed already formed. Macroscopically you cannot able to see, but it is happening. Okay. So equilibrium exactly means three things: thermal equilibrium, mechanical equilibrium, and chemical equilibrium. These are the three important points. If these 3 points are satisfied, your system or your process is in equilibrium. Again I am saying, if somebody will ask how you can say that your process has reached the equilibrium, then you have to say, I can able to say my process is in equilibrium if there will be no temperature gradient, if there will be no pressure gradient, if there will be no difference in chemical potential or difference in activity, as I told. Pressure gradient means what? Pressure is different. Okay, somewhere higher pressure is there, somewhere lower pressure will be there. If there is a difference in pressure, what will happen? Of course, species will migrate from high pressure region to low pressure region. It is not equilibrium actually, because they are moving now. Once they become equal, once the pressure become equal, nothing will move. That is equilibrium condition. That is called mechanical equilibrium, technically. Temperature gradient will be there. Suppose slag and metal have a difference in temperature. So then species can move from slag to metal or metal to slag, depends upon high temperature to low temperature. Species basically move from high temperature region to low temperature region. That is called diffusion actually, technically called. So if the temperature now becomes same, so it is again in thermal equilibrium. That is called thermal. Mechanical equilibrium understood. There will be no difference in the pressure. Temperature difference will be not there, means it is in thermal equilibrium. Now mechanical thermal. Now what is chemical equilibrium? I told you just chemical potential and activity. Once activity will become equal in two phase, once activity or chemical potential will become equal in two phase, nothing will move. Whatever it moved, already moved. Macroscopically, but microscopically they will be in equilibrium. They will moving and coming back, moving and coming back. Okay, so this is called equilibrium. Equilibrium means macroscopically there will be no change. Can you see? But microscopically the rate of forward reaction is equal to rate of backward reaction. And what do you mean by shifting the equilibrium? What do you mean by, I told you, what do you mean by shifting the equilibrium? You can shift the equilibrium to the right side, you can shift the equilibrium to the left side. But basically we always want to shift the equilibrium towards right because we want more products. or here we want to remove more phosphorus. So how equilibrium can be shifted? Same initiative principle, you have to disturb the system. If you disturb the system in the right side, or if you disturb the system, it will automatically move to this side. Let me give you a simple example. See, in the real industry, in the production of iron, in the real situation, they are continuously producing iron and taking it out. They are taking out the slag and metal continuously. It is not a like once they will produce and take out. No. Continuously this is happening. They are pouring the raw materials and taking out the products. So if you remove more amount of slag, what will happen? There will be a difference in chemical potential, of course. Because you are reducing the product side, so more product will form. You understand the point? So more product, because you have removed the products, so more product want to form, because least actual principle have to apply it there. So more products will form, you can produce more amount of iron. Suppose there are certain products which are in gaseous state, and you want to produce more product. What can be done? Yeah, this is do some mindstorming. Suppose this is a reactor. Listen carefully. This is a reactor. Okay, and the reaction is happening A plus B, and it will give rise to C. And C is a gas phase. Suppose this is solid. Solid, I can write like C also. Solid and solid. And this is a closed container. And you want to produce more C. What can be done? See, equilibrium is what? A will react with B and it will form C, and the rate of forward reaction and backward reaction will be equal. The C will form and decompose. C will form and decompose. This will continue. But sufficient amount of C will be initially there. Of course, some product has already formed. It will be there. Like a solid. So you want to produce more C. What can be done? See, the hint is this is a gas phase.
Sir, will increase pressure.
Increase the pressure. Okay, she is saying increase the pressure. Any from that side? You understood my question? A and B are in solid reactant. C is a product which is in gaseous phase. And you want to produce more C, because you cannot produce more C after some time, because they will reach equilibrium. No? Of course, the reaction will happen, they will reach equilibrium at that time. No more C will form. But you want to produce C, more C. The hint is C is a gas. C cold, you have to increase the pressure. Do some mindstorming. Yeah? Very good. You have to remove C. But if C can be removed, you are increasing the pressure or decreasing the pressure? Decreasing the pressure. So you have to attach a vacuum pump, simply. Just attach a vacuum pump will take away all the gas, that is C. So you have disturbed the system now. So equilibrium will shift towards right. So that's why I told, pressure is a very important parameter in thermodynamics. If you want to shift the equilibrium, change the pressure. Here what exactly we are doing? We are doing a process at low pressure. If you are doing a process at low pressure, you can produce more C with time. But what she told, there are certain processes where the product will be solid, but the reactant will be in the gaseous phase. Then what can be done? You increase the pressure. More pressure means more gas will be in there and more solid will form. It's very interesting. All are there in extractive metallurgy. We will study later. If I will teach you, that is very interesting. I don't know, I may not teach you, but that is one of my favorite subjects, extractive metallurgy. Shall I repeat or you understood? So, you can do metal extraction at low pressure also, at high pressure also. You have to see what is product and what is reactant phase, whether it is solid or whether it is gas. If products are gas phase, you do low pressure process, so that you can remove and equilibrium can be shifted to right. But if the product is a solid, but reactant are gaseous phase, then you apply high pressure, so that more C will form. Is it fine up to this? You understood the equilibrium? Because many people didn't understand. They graduate also, they didn't understand what is equilibrium. They will get confused. But they can only say rate of forward reaction is equal to rate of vacuum, because this is the full definition. So in simple word, you can say macroscopically the system is not showing any kind of change. But microscopically, in atomic level, on molecular level, it is happening. And it is happening in rate of forward is equal to rate of backward. Right? And equilibrium exactly means three things. It should be, the system should be in thermal equilibrium, the system should be in chemical equilibrium, the system should be in mechanical equilibrium. Mechanical equilibrium means pressure, thermal equilibrium means temperature, and chemical equilibrium means chemical potential. Okay? That means I can simply say the chemical potential of phosphorus in metal when equal to chemical potential of phosphorus in slag, they are in chemical equilibrium. Right? If the temperature of the metal equal to temperature of the slag, then they are in thermal equilibrium. Okay? If the pressure here is equal to pressure here, they are in mechanical equilibrium. Right? Is it okay? So in other way I can say, if you want to shift the equilibrium, you have to play with these three parameters. What are those parameters? Just tell me now. If you want to shift the equilibrium, one example I told you, pressure. Very good. What are the others? Temperature. Very good. And chemical potential. So one is temperature, one is pressure, one is chemical potential. Temperature. Pressure. This is chemical potential. So in other way I can say temperature of phosphorus is equal to temperature of phosphorus, but here it is suppose metal and this is slag. Now they are equal. So it's thermal equilibrium. Pressure of phosphorus equal to pressure of phosphorus. This is metal. This is slag. They are in mechanical equilibrium. Right? And chemical potential of phosphorus is equal to chemical potential of phosphorus. This is metal. This is slag. So they are in chemical equilibrium. So these three things should be satisfied. If they will not satisfy, one gradient will be exist. Reaction will happen. You cannot reach equilibrium in that condition. Any questions from this side? See, whatever I taught right now, this is important for steel making subject, this is important for extracting, this is important for a gate examination. Placement I cannot say, because those people don't know much deep inside the thing anyway, but it is important. Any questions? You can ask any simple question after this. You people understood feasibility, you have understood the equilibrium, then driving force. Okay, last, I will take 2 minutes. Fine. What is the driving force behind you are doing graduation right now? You want to get placed anyhow? Okay, you want to earn money after graduation, of course. That is your driving force. Actually, you want to earn money. You have a degree, you have knowledge, you apply for a job, you get a job, you earn money. So, to earn money is your driving force. Okay. So, similarly, whenever any process will happen, physical process or chemical process, if you want to do a chemical reaction, some driving force will be always there, or you have to provide some driving force. If driving force will be initially there, then that is a spontaneous process. You understand what? Spontaneous process means driving force is already available. That's why products are forming or something is moving, like sublimation is happening. Driving force is already available. But if in case of metal extraction, what you understood? Driving force is there, or we are providing some driving force? We are providing some driving force. It is not happening automatically. We have to provide some driving force. Either providing temperature or pressure or difference in chemical potential. These are the things. And last line, you have to remember, all the natural occurring process are irreversible process. You have to remember, all the natural occurring processes are irreversible in nature. Irreversible means what? Once it will form, it will not come back again. Right? Suppose water is flowing from overhead tank to your bucket. This is reversible or irreversible? Irreversible. But again you want to send it to the overhead tank. You have to attach a water. to send it back. That means you are doing some mechanical work, then only you are sending back. You are doing a reversible thing. Okay. So all natural occurring processes are irreversible. But if you want to reverse it, you have to spend some energy or you have to do some work. And the best example is your refrigerator. Your refrigerator, freeze, right? What it is doing? Freeze is cooling the items, whatever it is here. But outside temperature is higher. Inside the freeze the temperature is low. How it is low? Because you are doing mechanical working there actually. You are working on a compressor. The compressor will cool the system. But if you keep the freeze open, what will happen? For long interval of time, you keep the freeze open. What will happen? It will reach equilibrium. No? The temperature outside will be equal to the temperature inside the freeze now. Why this is happening? Because heat is transferring. There is a temperature difference. No? Outside temperature is high, inside the temperature of is less. So heat will migrate, heat will flow, and temperature will be uniform. Thermal gradient will not exist anymore. But if it is in closed form, it may stay sometimes. All are related: feasibility, equilibrium, driving force. Okay, we will discuss laws of thermodynamics in the coming lecture. You will definitely get a question from that, laws of thermodynamics.